A satellite meteorologist at the National Center for Atmospheric Research in Boulder, Colorado, leans forward over a bank of monitors displaying real-time thermal imagery captured from a NOAA polar orbiting satellite. The timestamp reads 4:47 a.m. Pacific Standard Time. She has been watching this particular formation since it emerged from the tropical waters near Hawaii roughly 60 hours ago, and in that time, something profound has shifted in the atmospheric architecture spreading across the northern Pacific. What began as a diffuse plume of elevated moisture has consolidated into a narrow, intensely concentrated corridor. The water vapor content in this feature now exceeds anything the automated tracking systems have flagged in this region during the past 18 months. Within 72 hours, this ribbon of moisture suspended in the upper atmosphere will make contact with the California coastline. And based on the velocity, depth, and orientation of its approach, the consequences could reshape entire watersheds, test the limits of infrastructure designed for an older climate, and force decisions that will reverberate through water management decisions across an entire state for years to come. The phenomenon visible on satellite imagery is what meteorologists call an atmospheric river. The term itself carries a quality of poetic precision that masks just how recently it entered scientific vocabulary. For most of human history, people experienced these events without having a name for them. Farmers in the Central Valley understood them as the sudden, catastrophic winter storms that could flood agricultural land without warning. Engineers building California's vast reservoir systems in the 20th century knew them as the extreme precipitation events that justified massive infrastructure investments. Indigenous communities across the Pacific coast recognized them as part of a cyclical rhythm of extreme winter weather that shaped seasonal patterns and survival strategies long before modern meteorology existed. But it was not until the early 1990s that scientists, building on research by pioneering atmospheric physicists, formalized the concept and gave it a name. Today, meteorologists define an atmospheric river as a narrow corridor of concentrated water vapor in the troposphere, typically originating in the subtropics or tropics and stretching poleward across thousands of miles of ocean. The water vapor content within one of these features can be staggering. A single strong atmospheric river can transport more water vapor than the Amazon River carries at its mouth. To put that in concrete terms, a modest atmospheric river moving across the Pacific toward California might be transporting the equivalent of 25 to 50 Mississippi rivers worth of water in vapor form through a corridor, sometimes less than 400 miles wide. When that incomprehensible quantity of moisture encounters mountainous terrain, physics takes over. The air containing the vapor is forced upward in a process meteorologists call orographic lift. As it ascends and pressure decreases, the air cools, and as it cools below its dew point temperature, the water vapor it carries begins to condense. The condensation is rapid and intense. What was suspended moisture transforms into liquid water almost instantaneously. The result is precipitation in quantities that strain the capacity of any hydrological system designed by human engineers. The windward slopes of California's Sierra Nevada mountain range and the coastal ranges of the Pacific Northwest experience some of the heaviest rainfall events recorded anywhere on the North American continent. These totals are not products of random meteorological chance. They are the inevitable consequence of geography meeting thermodynamics. A moisture-laden atmospheric river slamming into a wall of rock thousands of feet high creates conditions for hourly rainfall rates that can exceed 3 or 4 inches. Over the course of a storm event lasting 36 to 48 hours, these rates accumulate into precipitation totals that approach or exceed what some regions might receive in an entire year. Scientists have developed a ranking system to categorize atmospheric river intensity and potential impact. The scale, developed through collaboration between researchers at NOAA, the National Weather Service, and academic institutions including UCLA and Scripps Institution of Oceanography, runs from Category 1 through 5. A Category 1 event is characterized as weak, typically delivering precipitation in the beneficial range that agricultural regions depend upon for normal seasonal water supply requirements. These events arrive without particular hazard and often pass through regional consciousness without leaving significant marks on news cycles or formal disaster response systems. Moving upward through the scale, Category 2 and 3 events represent moderate to strong systems capable of producing significant precipitation, flooding of minor tributaries, and isolated infrastructure impacts that might affect particular communities, but do not rise to the level of widespread regional disruption or disaster. Category 4 events are where consequences begin to accumulate across entire watersheds. Heavy to extreme precipitation, major flooding of primary rivers, and infrastructure failures that disrupt water supplies or transportation networks become probable rather than possible. A Category 5 event occupies the upper boundary of what atmospheric physics can physically produce. These systems are genuinely rare but not unprecedented. They are defined by the capacity to produce catastrophic, prolonged flooding capable of displacing hundreds of thousands of people, destroying agricultural productivity across entire regions, and straining emergency response systems to the breaking point. The system currently tracking toward California is showing characteristics consistent with Category 3 to 4 conditions today. Meteorologists emphasize that this classification can shift in the final days before landfall. The exact intensity of these events depends on factors that remain sensitive to small-scale perturbations in atmospheric conditions, particularly the position and strength of the jet stream and the exact timing of when the moisture plume makes contact with California's terrain. The state's vulnerability to these events flows directly from its geography, and understanding that geography is essential to understanding why atmospheric rivers pose such a distinctive hazard to California specifically. The Sierra Nevada mountain range runs roughly north to south along the eastern edge of the Central Valley, a alignment of rock and ice that rises abruptly from valley floor at roughly 1,500 feet elevation to peaks exceeding 14,000 feet. This is one of the most dramatic topographic transitions in North America. When a moisture-laden atmospheric river approaches from the Pacific, it strikes this barrier and is forced upward almost immediately. The air rises, cools, and the water vapor condenses. Orographic enhancement, as meteorologists call it, amplifies precipitation on the windward slopes by a factor of 2, 3, sometimes even 4 times what would fall if the same atmospheric river passed over flat terrain. This geographic accident of plate tectonics and erosion has shaped California's entire relationship with water for geological ages. The highest rainfall totals recorded in North America have occurred in coastal California on slopes facing the Pacific. The permanent snowpack in the Sierra Nevada accumulates through precipitation driven largely by atmospheric rivers in winter months. The entire system of reservoirs built through the 20th century was designed with the assumption that seasonal patterns of precipitation and snowpack would remain relatively predictable. That assumption is now demonstrably wrong. The winter of 2023 illustrated the stakes with brutal clarity. Between late December 2022 and mid-January 2023, the state of California was struck by 9 atmospheric river events in rapid succession. Meteorologists refer to this clustering as an atmospheric river family, a situation in which successive storms arrive with insufficient spacing between them for watersheds to recover, for saturated soils to drain, or for swollen rivers to recede to manageable levels. The cumulative precipitation across the state during this 30-day period exceeded annual averages in some regions. The Russian River in Sonoma County, a stream that drains a basin roughly 1,800 square miles in area, reached flood stage 4 separate times. Levees along the Pajaro River in the agricultural lowlands of the Central Coast failed catastrophically. The town of Montecito, still recovering from a debris flow in 2017 that had killed 23 people and destroyed dozens of homes, was evacuated again as burn scars from previous wildfires amplified the risk of debris flows triggered by the intense rainfall. Statewide, the atmospheric river sequence was blamed for over 20 deaths and damage estimates exceeding $3 billion. Hydroelectric facilities shut down due to reservoir management constraints. Agricultural operations across the Central Valley lost unharvested crops to flooding. The experience created a cascade of cascading impacts that water managers are still working to understand. What made the 2023 sequence so dangerous was not primarily the intensity of any individual storm. Rather, it was the compounding saturation. A moderate atmospheric river arriving on already soaked ground can be more destructive than a stronger system arriving on dry soil. A second rainfall event in areas that have not yet drained from a first creates conditions where even small increases in runoff can overwhelm river channels that would handle each event separately without difficulty. This is the insight that has most directly changed how meteorologists and water managers now think about these systems. The danger lies not always in absolute precipitation amounts, but in the temporal clustering and the antecedent moisture conditions. Forecast models tracking the current system have incorporated this understanding directly into how they compute probabilistic risk. The models are now asking not merely how much rain will fall, but how much rain will fall given existing soil saturation, given current reservoir levels, given the snowpack situation in the higher elevations. These variables will ultimately determine whether the coming atmospheric river produces a manageable event or one that strains infrastructure and emergency response capabilities. Aircraft operated in coordination with NOAA's Weather Reconnaissance Program have been dispatched into the moisture plume ahead of the approaching system. These are the same aircraft that during hurricane season fly directly into tropical cyclones to measure wind speeds and pressure gradients at the center of the storms. During winter months in recent years, these reconnaissance missions have been redirected toward atmospheric rivers over the Pacific to improve forecast guidance. The aircraft carry instrumented sensors called dropsondes that are engineered to survive the harsh conditions of the upper atmosphere. These devices are deployed from altitudes of 10 to 30,000 feet. They fall through the atmosphere, taking measurements of temperature, humidity, pressure, and wind speed at multiple elevations as they descend toward the ocean surface. The data they collect is transmitted in real time via satellite to meteorological analysis centers where it is incorporated into forecast models. The mission over the past 48 hours has been to characterize the exact moisture content of the incoming plume, to measure wind speeds at different altitudes to assess how the moisture is being transported, and to track how the system is evolving as it approaches warmer waters that might intensify it further. What those reconnaissance flights are revealing is a plume of moisture that is unusually robust for this point in the calendar year. The precipitable water content, a measure of the total amount of water vapor in a column of atmosphere, is currently running at levels that would be more typical of midwinter months rather than the pre-storm period when this system first formed. The jet stream pattern steering the system across the Pacific represents another critical variable in determining what happens when the atmospheric river makes landfall. The jet stream is a river of fast-moving air in the upper atmosphere that steers weather systems across continents and oceans. Positioned at altitudes between 30 and 40,000 feet, jet streams circle the planet in roughly circular paths around each pole, though their positions shift dramatically with seasons and with variations in solar heating and ocean temperatures. A weak jet stream, or one oriented at a particular angle, can allow a storm to stall in place. A strong jet stream, or one oriented at a different angle, can push the same system across regions relatively quickly. A high-pressure ridge positioned in just the wrong location in the atmosphere can act like a dam, forcing an atmospheric river to sit nearly stationary over a watershed and deliver prolonged extreme precipitation concentrated over a geographic area that might normally expect that much rainfall spread across an entire season. This is the mechanism that is suspected to have amplified the impacts of the 2023 sequence. Meteorologists note that the current jet stream configuration appears more mobile than the pattern that dominated in January 2023. The high-pressure ridge that has been steering systems this winter is currently positioned in a way that would tend to favor a faster-moving storm with a shorter duration of peak intensity. However, meteorologists emphasize that this can change. The exact position of the jet stream in the final 48 to 72 hours before landfall remains sensitive to subtle perturbations in the current atmospheric state. Small shifts in the position of a high or low-pressure system can move the track of an incoming atmospheric river by dozens or even hundreds of miles, with dramatic consequences for which watersheds receive the heaviest rainfall. These shifts are not random. They follow from the fundamental physics of fluid dynamics in a rotating atmosphere, but their precise timing remains one of the most challenging aspects of weather prediction. The uncertainty about the exact track and timing and intensity of landfall is not a failure of modern meteorology. Rather, it reflects the genuinely chaotic nature of atmospheric dynamics at this particular scale. This is not a deficit of knowledge about physics, or failed instruments, or inadequate training. This is physics itself operating according to its fundamental principles. The atmosphere operates according to deterministic equations that are well understood and have been tested extensively. The outcomes of those equations, when run forward through time from an imperfectly observed initial state, diverge into multiple possibilities. This is why meteorologists now consistently frame probabilistic guidance in terms of ranges and likelihoods rather than certainties, communicating both the most likely scenario and the envelope of possible outcomes. A 5-day forecast for atmospheric river intensity and track might contain a range of possible outcomes, rather than a single deterministic prediction. Emergency planners must decide how to prepare when certainty is impossible. The standard guidance from Weather Service meteorologists to residents in vulnerable areas is now to prepare based on the highest probability scenarios, rather than waiting for a final confirmed forecast that may not firm up until the storm is already close. Residents near burn scars from recent wildfires face particular acute concerns. Fire removes the vegetation and root systems that normally stabilize hillsides. When intense rainfall falls on devegetated slopes, the soil loses its structural integrity. The result is debris flows, fast-moving slurries of mud, rock, and vegetation that can move at speeds exceeding 60 miles per hour downslope, destroying everything in their path. The debris flow in Montecito following the Thomas Fire in January 2018 remains a defining case study. 23 people died in a matter of minutes when a debris flow moved through the community following a brief but intense rainfall event. That event has shaped how California now thinks about the intersection of wildfire and atmospheric river risk. Water managers across California have been in intensive coordination with meteorological centers since the current system first became apparent on satellite imagery. The California Department of Water Resources, which operates a network of reservoirs across the state, has been adjusting reservoir releases in the days leading up to the storm's expected arrival. This practice is known as flood control operations. The logic is straightforward in principle, but complex in execution. Water is released ahead of an incoming atmospheric river to create additional storage capacity for the runoff that will follow the rainfall event. The balancing act is delicate. Release too little water, and a reservoir might be forced into emergency spillway operations during the storm, a scenario that played out dramatically at Oroville Dam in February 2017. Damage to the primary spillway during a major storm forced the evacuation of nearly 200,000 people downstream in what became one of the most dramatic near disasters in California's recent history. Release too much water too early, and the state risks squandering water it may desperately need if the following dry season proves severe. California's climate has increasingly taken on what scientists describe as hydroclimate whiplash. The state swings between extreme drought and extreme precipitation, with far less of the moderate, predictable seasonal variation that once defined normal years. A dry year following a wet year in which too much water was released can create crisis conditions if that water is needed for agricultural supply or municipal demands. This tension between flood control imperatives and water conservation imperatives has become a central challenge for water management in a warming climate. One innovation emerging from repeated confrontations between forecast science and operational water management is a practice known as forecast-informed reservoir operations, or FIRO. The concept is relatively straightforward. Rather than operating reservoirs according to fixed seasonal rules developed in an earlier climate, operators make release decisions based on high-confidence forecast guidance about what precipitation is likely in the coming days. If meteorological confidence in a forecast is high enough to guarantee space will not be needed for imminent flood control, the pilot program demonstrated that the approach could increase effective water storage at existing reservoirs by up to 10% without increasing flood risk. The success of the pilot has led to expansion at other reservoirs, including Lake Shasta, and limited implementation at some of California's largest reservoirs. This represents a quiet success born directly out of the state's repeated confrontations with atmospheric river extremes. The question of how atmospheric rivers might be changing in response to long-term climate warming is now a subject of intensive scientific investigation. Research published by scientists affiliated with UCLA and Scripps Institution has found that as global average temperatures rise, the atmosphere's capacity to hold water vapor increases following a well-established physical relationship known as the Clausius-Clapeyron equation. This is not a matter of theory or speculation. It is fundamental thermodynamics grounded in decades of laboratory observation and theoretical work. For every additional degree Celsius of atmospheric warming, the saturation vapor pressure increases by roughly 7%. In practical terms, this means that a warmer atmosphere can hold meaningfully more moisture. A global average warming of 2 degrees Celsius represents an increase in atmospheric water holding capacity of approximately 14%. Translate that into an atmospheric river context, and the implications become clear. When that additional moisture is funneled into an atmospheric river, the resulting precipitation event has the potential to be significantly more intense than a comparable storm would have been in a cooler climate. Several studies employing climate models to project future atmospheric river behavior over California have reached similar conclusions. While the total number of atmospheric river events might not increase dramatically, the proportion of extreme, high-intensity events is likely to grow. Some researchers have characterized this trend as a shift toward fewer but more dangerous storms. The physical logic is sound. If event frequency remains relatively constant, but intensity distribution shifts toward higher values, the result is a higher proportion of truly extreme events. Climate models projecting the remainder of the 21st century suggest this shift could become pronounced by mid-century, with some models indicating that Category 4 and 5 events might occur with frequency that would be considered rare under 20th century climate statistics. It is important to note what remains genuinely uncertain in this picture. The exact magnitude of the increase in atmospheric river intensity attributable to long-term warming varies significantly across different climate models and depends on assumptions about future greenhouse gas emissions. Researchers are still working to disentangle the influence of natural climate variability from the influence of long-term warming trends. El Niño and La Niña patterns in the Pacific Ocean exert profound influences on atmospheric river frequency and intensity over California on timescales of years to decades. Some individual atmospheric river seasons will be shaped far more by these oceanic patterns than by gradual warming trends. Attributing any single atmospheric river event entirely to climate change remains scientifically inappropriate, even as the broader statistical trend toward more intense extremes continues to accumulate supporting evidence. The evidence itself is genuinely mixed on some questions. Different climate models project different magnitudes of change. Some suggest atmospheric river intensity over California could increase by 20 to 30% by end of century. Others project smaller increases. A few models suggest precipitation patterns might shift in ways that could decrease intense atmospheric rivers over California while increasing them elsewhere. The honest scientific answer is that we know a warmer climate will make extreme precipitation events more intense, but we do not yet know precisely how much more intense, and we cannot predict exactly where those increases will be most pronounced. The regions that are most vulnerable to the approaching atmospheric river are, without exception, the same regions that have suffered most severely in past events. The Russian River watershed in Sonoma County, which drains rainfall from interior mountains to the Pacific through a river channel that is frequently overwhelmed by winter storms, has flooded so many times in recent decades that residents of communities like Gurneville have developed informal but well-practiced routines for responding. Residents move vehicles and furniture to higher ground before official evacuation orders are even issued. They understand, based on personal experience and intergenerational knowledge, roughly when the river will reach critical levels and what that means for their community. The Central Coast, particularly the agricultural lowlands surrounding the Pajaro and Salinas rivers, sits on some of the most productive farmland in the country. That land is also low-lying and historically prone to levee failure during major storm sequences. The Southern Sierra Nevada presents a different set of vulnerabilities. Any atmospheric river arriving on top of substantial existing snowpack raises the risk of rain-on-snow events. When warm rain falls directly onto existing snow, it rapidly melts it. The meltwater combines with the storm's own runoff to create discharge rates that exceed what rivers can carry. Some of the most severe floods in California's recorded history have resulted from this specific combination of atmospheric river and snowpack interaction. The geological record preserved in sediment layers across California reveals evidence of mega flood events far exceeding anything the state has experienced in its modern documented history. Researchers studying paleoclimate indicators have found evidence of flood sequences in the distant past that appear to represent atmospheric river events of extraordinary intensity and duration. The most famous example is the catastrophic sequence of storms in the winter of 1861 and 1862, a period that became known in disaster planning circles as the Arctic Storm, or the Great Flood. In the winter of 1861 to 1862, a prolonged sequence of atmospheric river events deposited unprecedented amounts of precipitation across California. The Central Valley, a vast agricultural plain normally hundreds of miles long and dozens of miles wide, essentially became an inland sea. Estimates suggest the water covered an area nearly 300 miles in length. The flood caused enormous damage to the nascent European settlement patterns and caused particular devastation to agricultural operations and transportation networks that were starting to develop across the state. Modern disaster planning models still use the 1861 to 1862 sequence as a benchmark for the outer limits of what a truly extreme atmospheric river event could do to a state that is now vastly more populated and economically dependent on agricultural productivity and water supply management. Indigenous communities across California recognize patterns in these extreme winter storms long before European contact or the development of modern meteorology. Archaeological and ethnographic evidence suggests that indigenous peoples developed sophisticated understanding of seasonal atmospheric patterns and the risk of extreme precipitation and flooding. They developed land use and settlement patterns that incorporated this knowledge. They built water management systems, including channels and reservoirs designed to capture and distribute the benefits of abundant winter precipitation while mitigating the dangers of extreme events. The existence of these systems demonstrates that indigenous peoples fully understood the reality of atmospheric rivers, even without the scientific terminology. As the current atmospheric river continues to organize over the Pacific and approaches the California coastline, its ultimate impact will depend on multiple factors that will not be fully resolved until the event is already underway. The exact track of the jet stream in the final hours before landfall remains sensitive to small-scale perturbations. The degree of orographic enhancement over the coastal ranges and Sierra Nevada will depend on wind speed and direction, factors that remain imperfectly predictable beyond 3 to 5 days. The amount of pre-existing soil saturation across different watersheds will determine how much additional runoff any given amount of precipitation produces. The interaction between rainfall at lower elevations and any existing snowpack at higher elevations remains a wild card that forecasters watch closely. What is not in question is the underlying physical reality that has shaped California's relationship with water for tens of thousands of years. The state's water supply, its agricultural economy, and its most severe natural disasters have always been bound together by the same phenomenon. A narrow corridor of tropical moisture, visible on satellite as a bright ribbon of thermal radiation, capable of delivering in the span of a few days more water than other regions, might accumulate across multiple months or years. That physics does not change. The geometry does not change. The vulnerability does not go away. Whether through adaptation, infrastructure investment, improved forecasting, or some combination of all three, California will continue to confront these events in the future. The scientific understanding of how these systems operate has advanced dramatically in recent decades. Researchers now use numerical weather prediction models, run on supercomputers, to simulate the behavior of atmospheric rivers days in advance. Satellite instruments measure water vapor with unprecedented precision. Aircraft reconnaissance missions collect in situ data from within the moisture plumes themselves. This revolution in observational and computational capacity has fundamentally improved lead times for warnings and has enabled water managers to make more informed operational decisions. Yet, for all this advancement, fundamental uncertainties remain. The chaotic nature of atmospheric dynamics means that small perturbations in initial conditions can lead to dramatically different outcomes days into the future. The heterogeneous terrain of California, with its complex mountain ranges and valleys, creates local variations in precipitation that are difficult to predict at fine scales. The interaction between different atmospheric layers and the response of the surface to precipitation remains an active area of scientific investigation. Against this backdrop of advancing knowledge and persisting uncertainty, California must continue to prepare for the next atmospheric river event whenever it arrives. The only question remaining is how well prepared it will be.